Good morning.
Good morning. I can hear you and I can see you well. Thank you.
Good morning.
Good morning, Buhle.
A warm welcome, ladies and gentlemen, to today's webinar. I'm Buhle Xakalashe, a Chief Engineer in the Pyrometallurgy Division at Mintech, and I'll be chairing this webinar. Our speaker for today is Dr. Karsten Zimmermann, all the way from Essen in Germany. Dr. Zimmermann holds various qualifications from a number of universities as follows: an MSc in Mine Surveying and Geodesy, and a Doctor of Engineering in Mine Surveying, both from TU Beck Academy, Freiberg, an MSc in Mine Surveying and Environmental Engineering from AGH, University of Science and Technology, and an MBA from FOM University of Applied Sciences for Economics and Management. He offers a broad line of services for measuring, prediction, and evaluation of ground movements, as well as operation monitoring of networks worldwide. Dr. Zimmermann specializes in applications which include, amongst others, subsidence and information forecasting, terrestrial and satellite-based radar interferometry measurements, a state-of-the-art tachymeter monitoring techniques, a 3D laser scanning and high-precision GNSS measurements, to mention a few. Furthermore, he provides high-end solutions for all kinds of geodetic and geomonitoring work using the in-house specially designed monitoring software called DMT Safeguard. He has licenses and certifications for expert of mining-related ground movements in the district of North Rhine-Westphalia in Germany. He has received honors and awards, including the Young Authors Award for Best Paper at the International Society for Mine Surveying in 2010. His skills include that of geomatics, geology, mineral exploration, coal, underground mining, geological mapping, mining engineering, geophysics, and minerals. He is currently the head of geotechnical monitoring and data management at DMT in Germany since 2014. Wow, what an impressive CV. And back to today's topic, which is an important theme of safety and risk management in mining. Dr. Zimmermann will be taking us through his talk entitled Integrated Tailings and Slope Monitoring. And for your info, ladies and gentlemen, the presentation will be circulated to the participants. And please kindly ask your questions on the chat or under Q&A. Guten Morgen, and over to you, Dr. Zimmermann, and looking forward to a highly informative and exciting presentation.
So thank you very much for the introduction. Warm welcome from Essen. I just start with sharing my screen here. I hope this works for the presentation.
We can see your presentation. Oh,
okay.
There we go. We can see your presentation.
Okay, that's the starting first slide of my presentation about the topic of mine tailings monitoring and slope monitoring, which is closely related. And we call the service we offer at DMT STINGS. STINGS is an acronym originally from an innovation project funded by the European Union, which has a very complex title: Supervision of Tailings by an Integrated Novel Approach to Combine Ground-Based and Spaceborne Sensor Data. So it's all about monitoring measurements on site at the tailing sites and integration of various data sources to gather useful information. Some words about myself. There has been a lot said already. So I studied mine surveying at Bergakademie Freiberg in Germany, and I'm currently the head of the geomonitoring and data management at DMT. So we deal with the listed topics, mainly geodetic, geophysical, geodetical measurements on site. For example, terrestrial and satellite-based radar interferometry, or 3D laser scanning, or GNSS, and related things. And we operate a dedicated monitoring platform, which is able to gather all sensor data on site in a unique integrated database, including then a visualization platform for our clients. Webinar agenda. I have 4 parts here. Please allow me. The first part is a small company presentation of DMT. Then I will, at the second part, I will introduce the tailing monitoring topic in general, and then I will talk about the technologies we can apply and use. And afterwards, we have a discussion, for example, about topics like operational demands for monitoring systems from your view, or legal requirements or technical requirements. So let's start with the company presentation. So DMT is an independent service provider for engineering services, consulting, exploration, geotechnics. We have a total of 30 branches worldwide, so we are operating internationally. We have about 1,000 employees. We have quite a high experience related especially to the mining topic, as we have been in the past in the research institute of the German mining industry. Today, a huge focus is on research and innovation. So DMT has currently or runs currently over 40 research and innovation projects, both funded by private institutions or by governmental bodies, by the European Union, for example. We have a quite informative campaign, which is called Engineering Performance, which you can check out on our website. We provide their stories with the view from our customer, a customer perspective on our services. Covers a wide area: electromobility, water sustainability, industrial engineering. So you can check this out on our website. These are our clients. You see we have the large clients on our site from the mining areas: Anglo American, Vale, for example, oil and gas, Total. We have also we are also internationally operate internationally, as you can see. For example, in Chile, we have contacts to Codelco, which I will go in detail in my slide.
We've lost you, Dr. Zimmermann, and we have lost your presentation as well.
Okay, I will try to share once again. So now it should work.
Thanks.
Yeah, for markets, plant engineering, process engineering. So plant engineering, we have basically we consult, we test, evaluate to plan and construct plants, industrial plants. We supply or help to supply systems and core components. We're taking care of the process engineering, installation and commissioning. Then we have a field, civil engineering and infrastructure. So here we help to develop complex infrastructural projects. We are active in the field of civil engineering, geotechnics, environmental engineering, surveying and monitoring, which is then related to the tailings topic again, and engineering geophysics. Energy is very important, so exploration of deposits and underground geology. We operate an own fleet of seismic vibration equipment, so as shown trucks, which we conduct large campaigns to investigate the underground, so data collection, processing, and then interpretation and modeling. And we have the mining field. And for the mining field, we basically, this is a very special service from our side. We cover the whole mine life cycle, so from exploration until closure of mines. Services are listed here on the right, and I want to especially mention our subsidiary company here in South Africa, DMT Kai Butler. You can contact Sodi Naika from Kai Butler. The email is given below regarding every service which is related to exploration and mining. Now I switch a little bit the topic, coming to monitoring, and here I present an example of a project we operate currently, which is a monitoring of an infrastructural object, a bridge, which is currently under reconstruction. So it's a quite large construction site, and our task is to monitor deformation or movement of bridge and construction components during the remediation works. And here we have installed over 500 sensors, which are water level gauges, inclination sensors, extension measurement devices, strain gauges, so-called total station measurements points. These are installed by us. The sensors, they are, each sensor is connected to the internet and sends data to our central database, which is included in our monitoring platform, DMT Safeguard, and which handles basically all the client data. This is illustrated here. So you see on the right side different sensors which are connectable to our database. They send the data to the database, and then the client sees basically a web front end with the latest monitoring data, and has also, for example, a map view to visualize the monitoring network, and gets, in case of an exceeded measurement value, exceeded threshold value, gets also an information alarm, a warning message directly on the construction site. Here it's shown here, the client sees on the right, for example, the bridge, and sees all the small icons for the sensors, which are green in this case. This means everything is okay, no threshold value is exceeded. And you can interactively zoom into this map to your object and check the sensor status online. And there's a variety of visualization options, so you can plot, make charts, bar charts, and so on, just to get a really inside impression of your monitoring data. So, and this brings us to the topic tailing monitoring. Some introduction slides at the beginning. So we have, if we look international, on an international scale, we have over 18,000 tailing facilities worldwide, according to databases. And there are the different types of tailing facilities, as you know, like embankments, piled up paste deposits, for example, dry deposits, or dams, yeah, which basically are integrated in the natural topography of the Earth's surface. And these are really large structures, dams, several kilometers in length. In this case, in Chile, on the bottom right, it's a dam at 2 kilometers length and has a height of about 100 meters. And the structure, the geometry of the dam constantly changes because the structure is increasing due to an increasing tailing. Some details here about a specific country, Chile. Chile is an important country for us since we have a pilot test site for our sting services here. And there we can count a high amount of tailing in general, so over 700 tailings, and a lot of them, the largest part is inactive or abandoned, and about 112 are currently active. And especially the not in operation tailings or the abandoned tailings, there's always a question: who is the owner, who is responsible? Is a risk management conducted? Who is taking care of financing of risk mitigation actions? And are they under observation or monitoring at all? These are questions which arise. Because, as you know, tailing operation, tailings, there's a risk involved, risk of failure. We had a lot of bad examples in the last years and also decades. This is an example here, well known from Bento Rodrigues iron ore tailing in Brazil, where the whole tailing dam structure collapsed, and which induced, of course, a massive impact on the environment and with fatalities unfortunately related as well. If we look at statistics, at some databases, we can see we have a significant amount of tailing failures over the last 100 years, which can be observed. You see here on the right, on the top right, North America, South America, Asia, EU, Africa. This is a statistic which only shows the reported cases, of course. There is most probably a high number of not reported tailing failures, which have to take account to. Also on the bottom right is shown the severity of tailing failures and over the last decades. And what can be seen that the severity, the impact increases over time because the tailing failure or the tailings increase in size, they get nearer to populated areas and so on. And you can actually calculate or find calculations of an average cost of a tailing failure in the literature, which is about 455 million euros in average. So this is basically a major key driving need to improve tailings monitoring is the financial risk involved in the tailing failure. And this graphic shows the annual expected cost for a tailing failure at different failure rates. In average, you can calculate an annual cost of about 275,000 euros per year, which a mining company would either have to save for the case of failure or have to invest in mitigation measures to help to improve and minimize accidents from the beginning. And so here all the sting services, tailing monitoring offers the technologies to do so. It can be seen in the international mining areas, countries that, of course, the governmental bodies, the authorities, know this issue, and they start to also form mitigation measures by applying, for example, national tailing policies. Here's an example from Chile. That means they create guidelines, programs, instruments, suitable instruments for the management of tailings. They start to form cooperations between institutions, between science and the mining industry. In Chile, we have the Programa Tranca, which is well known. It's funded by the Chilean government to improve tailing management. So it's all targeted to safety, to improve the safety for the public, for environmental protection, and as well to improve, for example, economy, circular economy, and also innovation in this field. And the same, I was a few months ago in India. The same can be seen in India. In an initial step, they start also now with a review of tailings management guidelines, which are available, and compile recommendations for improvement out of this. So lessons learned and then best practice guidelines to improve environmental safety and mitigating the risks. Okay, so now we come to the service in detail. I will detail the tailing monitoring technologies which are available in Stings. So the Stings service is basically a one-stop service for mine tailing monitoring, which integrates three key topics, which are stability control, substance release observation, and content monitoring into one unified monitoring system, one unified monitoring platform. And there's a partner network attached. So DMT is the key partner, the project lead or service lead for Stings service, and covering various topics like data integration and the data platform, which collects all the data, and also ground-based sensors, which I will tell about in a minute. Then we have a company, EFTAS, which is dealing with remote sensing, so radar remote sensing to detect ground deformation, to detect leakages, for example. We have university attached, which are dealing with stability modeling, for example. And we have local pilot site partners. For example, the University of Valparaiso is responsible for the Chilean market, establishing pilot sites and test sites. We have a university in Romania in Europe, dealing with a pilot site in Romania, and the same for the Geological Survey of Slovenia. There we have a pilot site in Slovenia. So the technologies we offer: geotechnical monitoring, which is basically providing a sensor network on site. We have radar remote sensing, which is processing of satellite data and analysis of satellite data. We have optical remote sensing, which uses also satellite data, optical images. We have stability modeling, so applying advanced modeling technologies to determine the stability of a tailing. We have geohydraulic modeling. There we have a special at DMT developed hydro toolbox, which allows modeling of various aspects. And we have the data integration topic, so collecting all available data in a unified platform. And this is how it looks in a drawing. So we have the geotechnical sensors, as you see here in the middle of the chart: remote sensing, stability model, hydraulic model. We have created special interfaces to connect database to these type of data which is available, information which comes out of the modeling, collect them in database, and then we have an analysis tool and a web front end which allows a customer, mining company or authority to have access to the data and visualize the data. So the platform solution is data acquisition at tailing site, data transmission to a central database, in-depth information analysis, online visualization, and then early warning or alarming in case of a threshold or exceeding a limit. And then we have also the reporting topic covered. So now I come to the specific technologies which are used or applicable in such a service. And I would start with geodetical monitoring technologies, which are GNSS, GPS, total station monitoring systems, terrestrial laser scanning, as well as ground-based radar. So let's start with GNSS, GPS systems. Within this project and service, we offer a special GPS measurement device, which is so-called low cost. So it can be applied in a high high number at the tailing site. This allows a point-wise movement and deformation control. So you have to install this device, the antenna, at a certain point of interest, and it will supply you with a coordinate information every 24 hours, every 12 hours, or every 6 hours. It's quite dense from the temporal information density. It's designed to be operated autarkic, so with a power supply from a battery and a solar panel. Has an integrated data transmission modem, so connects to the cell phone network, to Wi-Fi or to a local LoRa network, and then to the internet, and finally transmits the data to our servers. Processing is conducted automatically at our servers, and the results are presented on the web front end, which I will show also at the end of this presentation. Accuracy is quite high, so below 5 millimeters. So you can detect basically very small deformations at the tailing, and quite early detect some changes, settlements, and movements of certain objects of the tailing itself. This is an example here from our test site in Chile. So on the right, you see the equipment. It's a gray box here, which includes the electronics. The electronics are very small. The box mainly contains a battery and the solar panel, and you see the antenna. And here you see on the left a layout of the measurement network at our Chilean test site. You see we have placed here a total number of 12 sensors on the tailing, so on the top of the tailing in certain areas, and also we have reference point outside, which is shown here on the larger map, which basically provide a stable base for our measurement network. And here you can see an impression here on the left of our colleague during installation. And the client, what the client sees is basically the web front end, which is shown here, and then you can see the sensors which are in place on site. You can access the latest information and data. Green shows that we have currently no movement observed, so no risk involved. So going on to the next, I will get in detail on this a little bit later as well. Again, the next is total station monitoring. You see here on the top right, total station instrument, which is, or this technology is widely used in the infrastructural sector. Basically, you aim at target at slope here on the top right shown, or here also on the illustration from the open pit on the bottom. The instrument aims at this target at a certain interval, usually 10 to 20 minutes. It depends a little bit on the size of the network, and then transmits the data automatically again to our via internet to our servers. You have as well a very high accuracy, below 5 millimeters, and get a really accurate information about the displacement and movement of the target points at a tailing slope or at interesting objects at your tailing site. It's a very approved technology, can be integrated as well. And if you look in the high wall industry, for example, here in Germany and also worldwide, this is widely applied. So you see here on the left a container which includes a total station instrument with solar panel powering and so on. And the illustration on the right shows basically the measurement scheme. The instrument targets here on the high wall several points, and provides a continuous, very timely, dense information about possible point movements. And this can be, of course, combined. So total station measurement on the high wall can be combined with GPS, with the first instrument I showed you, and can be looked at or integrated to have a combined solution with improved accuracy and timely and temporal density. Next thing is technology is terrestrial laser scanning. So today we have a lot of new interesting equipment available. An example is the Regal scanner, long-range laser scanner, which are able to scan an object like a tailing slope from a very far distance up to several kilometers. There's currently a focus on campaign-wise measurements and the semi-automatic measurements, and to acquire a point cloud, a geometry of a target. Data is then transferred to an evaluation software, which allows basically to calculate deformations between several measurement campaigns. Accuracy is quite high, below 1 centimeter. What we're working on is to automate the system. So basically that you implement a laser scanner on site, and laser scanner regularly scans the slope and automatically detects deformation. This is a kind of a research question still going on. So as I said, the scanner is also connected to the internet here via cloud servers, and then the data can be automatically transferred to our database as well, and analysis can be conducted as shown, illustrated here on the right. Another technology is ground-based radar. This is a very widely applied technology, especially in the open pit mining with large high walls to observe high wall stability. And there are also several instruments available which use a radar signal, analysis of a radar signal, a reflection from the high wall to calculate displacements in line of sight. Here the results have to be interpreted in the right way, because they are influenced from the weather conditions, and especially also from the changing slope surface conditions like moisture on the slope and vegetation. But in general, it's very applicable technology as well. And again, these instruments are connected to the internet, to the database, and information is provided basically in a common database. And then we have, as a collection here on this slide, shown a variety of sensors which are available, especially not to detect only the surface changes, surface deformation, but also look into the structure, so into the tailing dam, mainly by placing sensors inside of boreholes after the tailing is built, or the best way is to already install sensor during the construction phase inside the tailing. So we have a lot of sensors, different types available: temperature, earth pressure cells, inclination measurement devices, water level sensors, microseismic sensors, for example, or seismic sensors, very important in earthquake-prone areas, for example in Chile, to observe microseismicity as well. And then we have video surveillance and so on. The important thing is to automate these sensors as well as all the others, so provide them with a robust digitalization unit, and then a data transmission unit to bring them into the database online. So now we switch a little bit from geotechnical sensors towards remote sensing. And here we can offer, first of all, radar remote sensing. So where we can use satellite images, analyze these satellite images in order to get a ground subsidence or ground settlement map of a large area. So we have several satellite systems available today. There's good quality data from an EU satellite system, which is called Sentinel-1, available for free. So the data is available for free. It has to be analyzed, of course. And also we have, let's say, higher quality commercial satellite systems available, like TerraSat-X, which offer a higher ground resolution, a little bit better in quality. They are not free of charge, so there are some costs related to each scene. And then these scene satellite images over time, you can collect them over, let's say, half a year, 1 year, collect a certain number of scenes, and then you can process them with various technologies. I will not go into detail. And what you get as a result, a large area map of the ground settlement or uplift of the area of interest. So it can show, as illustrated here below, stability, green. Then you get some areas which are possibly subsiding, settling, or stable or uplifting, whatever then you measure. The accuracy is quite high. You have centimeter level accuracy. Yeah, and this is a very suitable technology to isolate the hotspots. Let's say make a large area map and then isolate certain spots which are moving, and then there is the possibility, of course, to use it to install additional ground-based sensor and get a more detailed information of a certain point. We have another topic is optical remote sensing. So again, we use satellite images. This time we use optical images, and these images can be analyzed regarding their or spectrally analyzed, and this allows basically to analyze over a certain period of time a change, conduct a change detection, to detect, for example, soil moisture changes, vegetation changes, or changes in color. And this can be an indication for example, in a substance outflow of the tailing, and helps to determine critical risky areas at the tailing site. Another topic is, which is a little bit a science thing at the moment, is content monitoring or content evaluation. So optical images can be calibrated using samples, ground samples from the area regarding material, mineralogical components. They can be used to calibrate a satellite image or the processing algorithm, and they can help then to estimate the content inside the tailing or around the tailing regarding certain materials which are located at the site. Then we have stability modeling. So we can apply here advanced numerical analysis using finite element modeling, for example, to model the stabilities under certain or different scenarios. So we can use the geometry of a tailing, we can use the materials which are inside the tailing structure, and we can model, for example, different scenarios regarding filling, filling material, or the liquid level, the level height inside the tailing, and then calculate basically the risk areas or the areas with the highest pore pressure, for example, or the maximum shear strain increment at the tailing site. And we have done this here in Chile. As you see, we take the geometry, we have construction information from the archive of during the construction phase. We can build up a model with different materials, material layers and properties. Then we can calculate here in 2D and also in 3D the areas, for example, with the highest pressure. And this is an information which is very valuable, because you can then see where is the most risk-prone area, where do we need to install some monitoring equipment for really adequate or measurement of the actual deformation or actually pore pressure, for example. The same is valid for geohydraulic modeling. So you can build, similar to the finite element model, you can build such a model here with a hydraulic model. You can implement different material types of the tailing structure itself, and also of the tailing content. And then you can basically model the hydraulic potential where's the highest potential of an outflow of a tailing. You can also model over time the chemical composition, or better say the change of the chemical composition inside the tailing. And this all helps to estimate the risk. Related services are, for example, flood area modeling. So to model in the worst case, the area which is influenced by a tailing failure. Yeah, and also we can also help to consult regarding, for example, the cleaning of discharge of a tailing, so of an outflow. Yeah, let's come to the front end, which a mining company or authority gets access to with a password protected user account. And yeah, it's on a website. Yeah, it can be accessed from anywhere basically in the world. And you see here again the example from Chile, the tailing, and what is shown in red is the information from radar interferometry, from radar remote sensing regarding the large area ground information. You will see here a point measurement sensors at the tailing site in green. You can access the data, of course, online, and can look back in the archive and show the data of the last week, month, or year, for example. And you can see, of course, the latest measurement values, including the threshold values. And if a threshold value is exceeded, again, the mining companies or anybody who is involved gets an immediate alarm and alert message. There's interactive functionality integrated. If we look here again at the radar results, you can see here the abandoned tailing in Chile. You see the points, the available radar points which show settlement or uplift, and they can be color classified as to your needs. And what can be seen here, we have in the center small in green a portion which settles over time. You can also create here a cross section, and you see here a settlement inside the tailing. So this is an example of the functionality. What's also important, or turned out to be important, is a kind of direct information from the technician or from the people which are working at the tailing site. So what we have developed and can offer is a smartphone app which acts as another sensor, let's call it this way, which acts as a reporting tool. So a technician can take a picture of a risk area, of a critical situation, can comment and send it directly from the smartphone into the monitoring system as well. And it turns out here, or it is shown then as a geolocated warning point, which the management can look at for further risk evaluation. Okay, that's the end of my presentation. Stings mine tailing monitoring. I'm open for the discussion now. A small hint here: we have next year the DMT Mining Forum in Germany, in Berlin. It's a quite large mining conference, and also we will be there with a certain workshop or dedicated workshop regarding monitoring. And I would like to, or would hope to, that some of you can join this conference 2021 in Berlin as well. Thank you very much.
Thank you very much, Dr. Zimmermann, for such an exciting and informative presentation. We already have a few questions, so I'll start with the first one. In case of deformation in a tailings facility noticed, what are the plans of action from that point?
That's actually normally then set up with the client, so with the mining company together. I think there are a lot of parties involved related to an action plan in case of a critical observation or even failure. This is not part of this project. This has to be done in close cooperation with the mining authorities and everybody who is involved, and will be set up, of course, in a project, let's say.
Good, thanks for that answer. So the next question, so relating then to the integrated solution that you've presented at the end, what is the approximate cost of employing this technology?
I cannot give you an exact number, but this depends on the amount of data which we have to handle. This can be very cheap if we are talking about only one sensor, let's say, and this can be also be very expensive if we're talking about thousands of sensors and several hundred of data sources we have to integrate. This is, the calculation is of course project dependent, and we can discuss it in a in an individual meeting.
Okay, thanks for that one. The next question is, when is the right time to start monitoring tailings dams?
Basically, the right time is to start with setting up a monitoring concept at the beginning of the planning, of the tailing planning. So because you have a lot of monitoring equipment and sensors which give the most information, which they are integrated into the tailing structure. So basically, if you construct a tailing from scratch, you have already to think about implementing the right monitoring technologies.
Okay, thanks for that one. So then there's a follow-up question from my side from that good question. So how closely involved are you in the design of new facilities? So this is then along the lines of predictive design.
Yeah, we are currently involved only in our monitoring of existing tailings, but we are working on cooperations which with construction companies and with mining companies to get involved as early as possible, because this improves the quality of the monitoring network and monitoring results at the end.
Okay, thanks for that. So you mentioned existing tailings facilities. So there's a question and a comment from my side. In extractive metallurgy, we are interested in value reclamation from tailings, and some of these tailings are stored in dams, such as red mud from alumina production. So I've seen you did actually show a facility in Germany then. However, catastrophic failures of these containment facilities have been reported over the years, as you have also mentioned in your presentation. So have you received more queries then from in light of this?
I can go back. We have we were in, or I was for 2 weeks in India last year, and this is an example. You mentioned red mud, and
correct.
Yeah, I don't know if this answers your question, but this is related perhaps. Red mud tailings in India and also worldwide are a source of risk, of course, in India, because main reason is that we changed the composition of the tailing material, going from wet slurry to dry slurry or sludge, because of newly available filtration technologies. So the material changes, and this is a reason or a reason for increased risk for increased failure observed lately also in India. So this has to be take care of this by applying stability modeling, not only once in the tailing construction phase or planning phase, but also during tailing operation. Yeah, just to adjust the parameters to new circumstances. For example, going from wet material to dry material. I hope this answers your question.
Okay, thanks. So there's a question then along these lines as well. So this question reads as follows. The presentation showed how the monitoring is conducted, but very little information was given on how this is used to prevent failure. Has DMT gotten any case studies where they can show that?
We have started to look in databases which show history. So which shows, for example, what are the main reasons for a tailing failure, and then accordingly implemented the measurement technologies. So, for example, a main failure reason is overtopping by a mismanagement, filling it simply too high, or by for example, weather events, natural causes, heavy rain events, which causes overtopping. And of course, reasonable monitoring approach would be to monitoring the volume and the filling state of the tailing. And this is what we took from the past, and then we implemented the right strategy to provide a suitable monitoring. Hope this answers your question.
Yes, thanks for a comprehensive answer. Thanks for an excellent presentation once again. Are you using or have considered using fiber optic sensors as part of the sensing technology applied?
Absolutely. We are using it not in this tailing topic, but in other infrastructural monitoring applications. And this is, of course, a topic for tailing monitoring. Can be integrated here as another monitoring technology. Perfectly right.
Okay, thanks. Where do we place drone surveying in monitoring?
It's also applicable. We have used drones extensively in other projects, also related to slope stability modeling in mining. So we use drones mainly for determine an accurate 3D model of the slope or open pit geometry. This was, of course, very fruitful data we gathered, which can be used then, for example, to set up or help to set up the geometry for stability modeling.
Okay, thanks, Dr. Zimmermann. What is the maximum monitoring radius of the technology?
Yeah, it depends on the technology, on the applied systems. If we look, for example, at remote sensing, we can use satellite scenes, which are several square kilometers in size. So each scene covers a really large area, and the scenes can be also connected together to gather basically a whole country, cover a whole country with information. And this is especially interesting for abandoned tailings, because abandoned tailings are often widespread over a country, and you need a technology which can cover these small dots in a huge area in a measurement. And one is remote sensing. All the other things are, of course, point-wise. If we look at GPS, there's a point-wise installation on a dedicated point. If we look at laser scanning, you have a range of several kilometers. So we can go from the smallest detail from a point-wise measurement into a really large-scale, country area observation.
Many thanks. What is the life of the technology infrastructure?
Yeah, from experience, the equipment is quite sophisticated sensor equipment, equipment which is installed inside a tailing on a borehole, usually has a very long year lifespan. Yeah, also the measurement instruments like a total station, also they are designed for outdoor use and have also several years of life period. It's also then with experience from the mining area, you can construct a certain housing and protection housings to extend the lifetime. So, yeah, I hope this answers your question.
Yes, no, thanks for that answer. Now going to the topic of data. How do you work or use the newly developed world database of mine tailing dams? And how important is the global database in your opinion in this?
Yeah, we don't integrate the database directly. The database was used by us to get information about, for example, the distribution of tailings worldwide, numbers, use, main failure reasons, severity estimates and numbers and so on, just to tailor the stings monitoring service. But we are open we have an open data interface with our database. So if there's data which is reasonable or suitable or even necessary for conducting certain tasks, we can easily connect also external data sources such as a tailing database.
Okay, thanks. So there's a follow-up question from my side. Data seems to play a key role in your systems. Could you say a few words about the opportunities presented by big data and the era of the fourth industrial revolution on your offered solutions?
I think we are not talking about big data in these cases, because big data is a much higher level of information that is collected here in this system. We are talking here about simple data streams, might be also in a very dense interval of 500 Hertz if we're talking about seismic data, or satellite scenes, which are, of course, if you can combine them, have a very high number of high in size in total, but I think this is not really a big data application. What it is definitely is the topic AI. So artificial intelligence, to analyze the data not only analytically but also with artificial means. For example, if you collect seismographic or geophone data, vibration data, this has to be analyzed and classified. Is a real earthquake? Does this vibration come from inside the tailing or from outside, or is it just a truck passing by? And here you can use AI, and we are working together with Microsoft in a project to determine how artificial intelligence methods can support, for example, classification of microseismic events.
Thanks for the clarity, and thanks for the comprehensive answer as well. From a geotechnical point of view, do drier tailings result in a longer life of complex? We've lost no, okay.
Yeah.
Yeah, you're back. Thanks. Let me repeat the question. From a geotechnical point of view, do drier tailings result in a longer life of complex?
That depends. You cannot give a clear answer here. This is always a question of a lot of influence factors. A dry tailing can also be very vulnerable if we are talking about natural disasters like a heavy rain event. A dry tailing can be vulnerable regarding, for example, such an incident than another tailing type. This has to be looked individually. Each tailing basically has to be evaluated individually.
Okay, thanks for that answer. The next question, have you worked with mixing the tailings material and waste rock? If yes, could you comment about it?
You are talking about to optimize the, let's say, the content by,
Absolutely.
of course, this has an advantage. The problem here is with stability, and then also stability modeling is the uncertainty of the components in the tailing and material properties, and also the location, as it is here, for example, with red mud. Yeah, you have then dry components, and then you have certain spots which are wet and have totally different composition and stability parameters than the rest of the tailing. So basically, this would improve the modeling accuracy if you have a unique property and unique distribution of material inside a tailing pond. But again, has to be analyzed and as an input into a modeling individually for each case. But in general can be given this remark.
Thanks for that answer. Does the MT think this type of monitoring will become legislated by governments in the future?
Absolutely. So the example is for example, Tranca project in Chile, which is a governmental funded and initiated project to improve tailing management monitoring. And this has a clear target to set a framework and requirements for authorities or for the mining industry in the final step, how to monitor the tailing. What are the requirements and what are the obligations for a monitoring network? And Stings plays here a kind of supportive role. Stings can offer the suitable monitoring technologies which are in accordance to later legal requirements.
Thanks for that answer. A question from Mark Button is not so clear, but the question is, what type of unit is that? Is it an inclinometer? So this question came about when you were discussing the when you were talking about the technologies on offer. So it was just before slide 33, around about that time.
This slide? 33, also, okay, moment. No, I talked about GPS, which is this device, which basically is yeah, a GPS to determine your position, and you can do it in a very accurate way, like with this device, to get millimeter accuracy, and then detect the changes in position of a certain point, where basically the antenna is installed. That I talked about this, and then I mentioned inclination measurement devices. Inclination measurement devices can be connected, for example, on objects at the tailing, for example, and some steel probes on top of the tailing, but are most suitable to be integrated inside the tailing dam or the tailing structure, either permanent or can also be in boreholes, can be measured campaign-wise, the inclination, to get an information about changes over time in the tailing structure.
For the detailed answer. The next question is the opportunity to turn on pumps when piezometric surface reaches a critical level and thus reduce pore pressures?
Yeah, monitoring system has to observe the filling level inside a tailing pond, if we're talking about these liquid tailing ponds, and there are some limit values which are derived from the modeling, stability modeling, and these limit values in the filling height of the tailing have to be observed. And then the monitoring system, the database, can be directly connected to a pumping system, for example, which pumps in case of an increased level liquid outside of the tailing.
Okay, thanks. The next question: how can you make dry tailing solutions be applied on high rainfall climate?
Oh, I don't understand this question. I have not. Can you please repeat?
So how to make the dry tailings be applied on a high rainfall climate? So it's probably saying then solutions that are tailored for dry tailings in an event that there's high rainfall and then you have a very high moisture content, or you have now wet tailings. How can you make this applicable?
I have to be honestly said, I cannot really answer this question. An idea would be a dry tailing to cover it, make it waterproof, let's say, from the cover, and then in this way to stabilize it. But I cannot really answer this question.
Okay, thanks. So the next question is your system integrated into the European Union Sentinel, or you have to download the publicly available data for use each time?
Yeah, it's a semi-automation, I would call it. You have the data is of course not manually downloaded. But a specialist has to set up the scheme of scenes which are necessary or which are required in this case, and then the processing system would automatically download from the EU server, of course. So it's highly automated, but there's of course a person needed, a specialist needed to administrate such a system.
Okay, thanks. So the next question is, one critical proactive measure in tailings operations is to monitor the dry beach length, which affects the pore pressure in the dam. So which of the sensors is used then to monitor this? And where is the monitoring done?
You have to select one of these. I don't understand the question correctly. I hope I understand it. We have piezometer pressure sensors, and we have the basically water level sensors, which are in combination delivering the results that you want, as I understand it right now.
Okay, thanks a million times, Dr. Zimmermann. We have also reached now, it's 11:05, and Jack, we have answered all the questions. Thanks a million times, and thanks a lot to the attendees for the enthusiasm.
Thank you very much.
Yeah, thanks a lot. Cheers then.
Bye-bye. Thank you.